Welcome to Careless Coder, and today we will continue our ARM64 Linux assembly tutorial. Here is a little Pi 4 with ARM64 Linux on there. And let's jump in and code a little program that takes the contents of a register and prints it in decimal format on the screen. We're not going to cheat like all the other channels do and import printf. We're going to actually write it low level ourselves. So let's jump in and have some fun with ARM64 assembly. Motherfucker! So first we're going to set up the boilerplate to make the assembler happy. The text segment contains the code. We need to align it to 8 bytes. And the entry is always underscore start. Underscore start. We're going to create our print method, and for the first time we're going to use the stack. So what we're doing here is we store the frame pointer and the stack pointer on the stack. The reason for this is when you have nested calls to this print function, you need to keep all those stack frames in place. We're also going to store all the variables that we're going to overwrite. So in this case that's an x2 and an x8. Now we need to pop them from the stack, and we do that in reverse order. And it doesn't matter which two registers you put in here, as long as you are consistent when pushing them on the stack and popping them off the stack. This could be x10 and x1, that's perfectly fine. And there is something very important that we need to do. We need to put an exclamation mark in here. That is the so-called write back. So as soon as we say we have the stack pointer with an offset minus 16 bytes, these are two 8-byte values, then update the stack pointer. And you can only do a write back with 16 bytes offsets. And here we're saying just add back the 16 to the stack pointer. And now we can safely return. So now we have a function that always preserves all the registers that it's going to change, and that is the safest approach that we can do. Now we're going to write the code that we did last week or the last time. We're going to say that we're going to print to standard out. X0 points to the file descriptor, and we're going to say that we want to call the system write call, which is 64, and then we're going to actually call that system vector. So now we just created our print function that we did in the previous tutorial, but now we keep a stack, and that is the clean way. Now we're going to need to define some variables. That goes into the data, and let's also do align that on 8 bytes, and we need a character variable that is 1 byte long, because print actually points x1 to a pointer that contains the string. And we want a value to print. So let's say the value is 65535. And let's also make some strings as bit count. Okay. Let's first write our decimal printing routine. We call it print unsigned integer, and there we're going to also store everything on the stack. And what we're going to be using are a lot of variables in this case. X0, we're going to be using... And these numbers are arbitrary. You just pick what you need and what doesn't conflict with other things in your code. And I need one more. We're going to also store X0 and X1. Immediately do the LDRs. Let's copy that. And now we can safely return. Let me explain the algorithm for printing a digit in decimal onto the screen. For example, X0 has 1 to 6. Then we're going to divide that by 10. And you will see that the remainder will be 6. We're going to push that onto the stack. Then we have 12 and we divide that again by 10. Then the remainder is 2. We're going to push that on the stack. And then it's 1 and divide that by 10. And then 1 is the remainder, we push that on the stack. So we're going to use the stack for our local storage of a 128 byte array to hold the digits that we're going to print to the screen. And we can ourselves manage the offsets with offset registers, X5 for example, and print it in reverse. And that is what we need. So we need to divide something by 10, so we set X7 to 10. We need a counter to tell us how many bytes we have written on the stack, and we use that counter also as an offset pointer on the stack. Let's use X5 for that, and we initialize that to 0. And then we need some space on the stack to basically grow up. So what we can do is we can take this stack pointer, and from the stack pointer we subtract 128 bytes, should be enough. And whenever changing the stack pointer, immediately below we turn back the stack to its original state. Otherwise you forget and you're screwed. Alright. So now we're going to need to handle a special case, because if the value is 0, we divide it by 0, the remainder is 0, it would break the logic of the algorithm. So if X0 is 0, we have a special case that we're going to handle here, which is actually forcing a 0 on the stack manually. So compare X0 with 0, branch eagle, then we're going to print uint 0. Which we do here. Print uint 0, not 0, but 0. We're going to offset the stack pointer by 1, so adding 1 to X5, basically going the stack from minus 128 to minus 127 now. Because we're going to store a byte that is in W0, that is the lowest part of the X0, the lowest 32 bits of the X0 register, and we're only storing the byte, so the only first 8 bits. And we're going to store that to the stack pointer, offset by X5. Okay, cool. Now we need to do the pushing to the stack. Let's call that print uint count, because we're going to count the number of bytes that we push on the stack. Here we're going to use the division. udiv is unsigned integer division, and we want that result in X2. We're going to divide X0 by 10. And on Intel, you are done now. You have a remainder and your quotient. I hope I say that right. on ARM assembler we need to do an M sub as well. We want the remainder in x3, we want the quotient in x2, and we're going to use x7 and x0. I could actually immediately push it into x0, I'm thinking about it, but let's keep it for this now. We're going to offset the stack pointer by 1. We're going to store the byte that is now in W3, that is the remainder, the thing that is behind the comma. We're going to store W3, because it's a byte, we need to do W3. We're going to store that to the stack pointer, offset by x5. And since each time we increment x5, we also offset the stack pointer by x5 bytes. I hope that makes sense. Basically, we're keeping the stack pointer at minus 128 and we write to minus 127, minus 126, minus 125. And then we're just going to count back and print them to the screen. Alright, so that should be that. And now we need to actually move the remainder back. That's why I said I could have probably used x0 immediately here. Alright, and if x0 equals to 0, then we're done. Then we can print what is on the stack. And otherwise we need to continue doing this. Alright. And otherwise we need to branch to print uint print. Print uint print. Right. Okay. Let me think. Yes, we need to now store in our variable that we created below. Here we need to store that value that is on the stack. So we're going to load from the stack in W3. We can do that. We used that before. On offset x5. Since 5, in case if we're using x0 with the value 126 is still 3, we're basically pointing to 125. We need to do some arithmetic on here. We need to convert the digit to the ASCII number. And we do that by adding 48, because 48 is the ASCII value of 0, 49 is the ASCII value of 1. And now we can store that byte to I need to also load x here for a second. Load x1 points to the character, and then we can store w3 to x1. Basically preparing to call the print statement. And we need to set x2, that tells the number of bytes to print to 1. And then we can call print. So basically what we're doing is we're getting the character from the stack, we're adding 48 to it and pushing it in the variable, in the car variable. And then we're calling the print function and telling the print function to only print one character that is in the car variable. Then we need to subs from x5, 1, and we need to repeat this until x5 is 0. And otherwise we're done. So let's move, let's load in x0 the value that is value, and let's call print uint, then normal exit, bl exit. Let's see if this compiles. Of course we made an error. Undefined exit. Oh, I didn't write my exit program. Since the exit never returns, there is no reason for setting up a stack. That would be silly. So we're just going to, what was it again? Let me have a brief look. I forgot it. I believe it was 96, 93. System call 93, and then we call the service. And actually even the return would be unsensical. We're never going to return, but I always put that in. What else is wrong? Oh, there's nothing wrong. Bit count. And there we go. We have written the value 65535 to the screen on a low-level way. And let's change this to, for example, 126. The running example we did verbally all the time, 126. So we can write now values to the screen. Let's write a little function that counts the number of set bits in a value that is in x0 and show that on the screen as well. 65535. We already have the strings here. Let's set up the program to first print the first string, bit count. The length of the bit count is the len as bit count, we call it. And then we're going to call the print function. And then we're going to load in x0 our value, sorry. Then we're going to load in x0 the value that we want to count the number of bits from. And we're going to do actually a print unit. So what we're actually doing now is we're going to first print the message that says we are counting the number of bits set in number. Then we're going to print the number that we have validated actually words. Then we're going to print the second part of the string. And let's do the syntax on. So now we print the second part, and then we're going to call our bit count function that we're going to write now. And we're going again to print the uint function, and then we're going to exit. So how to do a efficient bit count. There is an algorithm made by Mr. Kernighan, also involved in C and Unix. And it basically does the following. N, that's the number of bits, equals n minus 1. And you repeat that until if n 0, then that is basically the Kernighan bit count algorithm. We're going to store the stack and the registers that we're going to be using. And we immediately make sure that we pop them off in the reversed order so we can't forget. And return. The reason I'm adding the bit count is to drive home this whole stack pointer thing and saving your registers that you're going to use. We're going to set... we first need to compare if x is 0. If it is, we can branch to bit count exit, then we're done. So let's make this bit count exit. We need a counter. Let's use x2. x2 set to 0 as our bit counter. And this will be the bit count counter loop. I like to have that separated. We need to tell the counter to increment by 1. If we in this part, then 1 bit is set. So x2 contains the bits that we're counting. Then we need to subtract and put the result in x1 from x0, the value minus value 1 minus 1. We could do an add minus 1. And then we need to do the AND. We want the result in x0. We want x0 to be AND by x1, like we said here. So this statement is n equals the end of the... let me write that out a bit cleaner, and like this. And as long as x0 is not 0 and the AND already works on the 0 flag, then we keep counting, because then there are still bits set. So this should do the bit count thing. And of course there is an error. I see it. There is an extra comma here. And that's not correct, because I know there's 16 bits set, so there is an error somewhere in my ways. And since I want the result in x0, I need to move the counter of the number bits set from x2 into x0. And now it should work. And there we go, 16 bits set, and that is absolutely correct. And if we do 1, there should be 1 bit set. So that is working. So we covered a lot of stuff today. It's a very in-depth tutorial. Usually you see people cheating in these tutorials, that they use the printf statement to print characters to the screen. I figured that this was the best way to actually illustrate how to use the stack by actually creating a decimal print function ourselves. We talked about the STP that allows you to store 2 arbitrary registers onto the stack, offsetting them by 16 bytes, and the write back, the exclamation mark, updating the SP, and that can only be done with 16 byte offsets. So if you use the str to only store 1 register and you want to do the write back, you still need to offset it by 16 bytes. That's why I subtracted 28 from the stack pointer, basically creating a 128 bytes local array that we put in the individual digits, and we print those digits in reverse back to the screen. And then we briefly touched upon the bit count algorithm by Mr. Kernighan, the most efficient way to count the number of set bits, because you only go through that loop the amount of times that there are actually set bits. So I hope you learned something, and I hope to see you in the next one.